Okay, we're going to go back to trig substitutions, but first I need to talk about completing the square, because sometimes that's going to be necessary. So let's recall what you used to do. So if you had something like this, sometimes you were asked to complete the square. So you would take half of your 8, which was 4, and square it and add it to both sides, right? So you would get x squared plus 8x plus 16 equals the 16. So this 16 is over here. This makes a complete square of x plus 4 squared. Okay, that was when we had an equation when we could add to both sides. So now we're going to complete the square without an equation. So what math people like to do is we'd like to say x is equal to x plus 16 minus 16. It's still x, right? Adding and subtracting. So that is a trick to keep it the same. So that's the add and subtract. Okay, so if I've got x squared plus 8x, no equation. So if I want to complete the square, I take half of the 8. I'm going to add and subtract the 16. These 3 here make my complete square, right? X plus 4 squared gives me x squared plus 8x plus 16. And this negative 16 just hangs on at the end. Let's do it again. So if I've got this and I want to complete the square, so this 5, I'm just carrying along at the end. It's not part of me completing the square. I'm going to take half of my negative 6, which is a negative 3, and square it. So I'm going to add and subtract my 9. These 3 things here give me x minus 3 squared. Then I'm going to have this subtract 9 and plus 5, and that's going to give me a negative 4 at the end. Okay, so that's completing the square without an equation. So let's remind ourselves there's a rule about completing the square that the coefficient of the x squared term has to be a positive 1. So if I'm asked to complete the square on something like this, so first I would rewrite it like this. Then I would want to take and factor that negative sign out of the first 2 terms. This positive 1 just carrying along at the end. Okay. So now I'm going to take half of this negative 8 and square it, and then I'm going to add it and subtract it, right? So I'm going to take this half of negative 8 would be negative 4, add and subtract. Oops, let me move this up a bit here. So I'm going to add and subtract. But let's look at it. As I add the 16, which I need because I need to make this the square, this negative sign says, oh, but you're really subtracting a 16. So I'm going to add the 16, and this 1 carries along from the outside. So let me go over that again. So since I'm adding 16 to make the square, this negative sign on the front, right here again, says I'm really subtracting 16, so I have to add 16. This 1 carries along from before. So this gives me, with the negative in front, x minus 4 quantity squared plus the 17. Shoo! Okay, so now let's make it really confusing. Let's add a radical and put it in the integral. Okay, here we go. So here it is. So I'm looking at this, and the reason I'm motivated to complete the square is I'm noticing I've got a square root. Wouldn't it be nice if I had an a squared minus an x squared, or an x squared minus an a squared, so I could do a trig substitution? So that's why I'm motivated to do this complete the square. So first things first, rewrite this so the x squared is in the front, and you factor the negative out. Has to be factored out of the first 2 terms. This happens to not have a constant term, right? So I'm going to take half of my negative 4, which is negative 2, square it, which is 4. So I added 4. Oh, but I really subtracted 4, so I add 4. So then this gives me the complete square of x minus 2 squared. Keep the negative out in the front, and then this plus 4 is at the end. So whenever I see there's a negative sign here, I put it in the middle. I would encourage you to do the same because it will help you to see what the pattern is of what substitution to do. So this here, me working all this up here, changes to 4 minus x minus 2 squared dx. I'm going to suggest you do an easy u substitution, u equaling x minus 2, and so then you can see the du is just dx. So this turns into this. Much easier to do the integral of, and you recognize it right now as the trig substitution of sine. So you're going to say u, right, starting with the letter u, not x, equals 2 sine theta. Remember, always take the derivative right away. So du is 2 cosine theta d theta. So let's change this all from u's to thetas. Remember, it should get large. So 4 minus u squared, so putting this in for u, so I get 4 sine squared theta. Du, remember, gets replaced by a big thing of 2 cosine theta d theta. Okay, the reason we do this trig substitution is to get rid of the radical. So there should be an identity happening in here. So let me I skip some steps here. So I can say root 4 root 1 minus sine squared, right? And then this turns into a 2, and this turns into a cosine squared underneath the radical. So underneath the radical, squaring, undoing the square gives me 2 cosine. So this here turns into 2 cosine theta. This 2 cosine carries along, and then the d theta. So now I get 4, pull the numbers on the outside, I get cosine squared. How am I going to do that integral? Oh yeah, half angle formula, you know it. So rewrite cosine squared as 1/2, so that changes the 4 to a 2, 1 plus cosine of 2 theta. Then I'm going to take the integral of 1 with respect to theta, so I get theta. Antiderivative here, La Jolla theorem, 1/2 sine of 2 theta. Remember, sine of 2 theta, you must use this identity. You must. You don't have a choice. You must use this identity. So I'm going to replace this with 2 sine cosine. So the 2 sine cosine with the 1/2. Oops, the 1/2 and the 2 should cancel, right? So that shouldn't be here. Oh no, sorry, it is there because I guess I multiplied this 2 in. So 2 theta, 2 times this, right? The 2 and the 2's canceled, but then this 2 comes here, and that's what this is. Okay, now it's triangle time. Where does the triangle come from again? The original substitution. The original substitution of u over 2 is sine of theta. So if my theta is here, opposite over hypotenuse, this side here should be your little happy moment. That's right, that was in my original integral. So now I'm going back to solve for this, right? So theta, that's the only time you do the inverse, right? So I do the inverse of this, inverse sine of both sides, right? Inverse sine of u over 2 is theta. That's what this is. Then I'm going to find out what the sine of theta is and what the cosine of theta is. Sine of theta is u over 2. Cosine of theta, adjacent over hypotenuse. And then I just didn't write the last step of putting the x's back in, right? So that would be 2 inverse sine, and so I would put in the x minus 2 over 2 plus, and let's cancel these 2's, so I would have x minus 2, 4 minus x minus 2 squared over 2 plus c, and then you'd be done.